Yes. Yes. 0.5 is another method that you apply those constant coefficients using so-called operator. So just one method would be enough. And take care of that. I'm not going to use those. Okay, so that's a variation of parameters method. So as I talk about it, the idea is we're going to use it in order to get the particular solution of a homogeneous equation, okay? So we are going to give you, I name this method, and you apply the variation of the parameter for the differential equation. Or otherwise, you will find out if you want to solve it, if you get a constant coefficient, you go for it. You find the YC. You want to find the YP, you look at the function. If the function is of type of polynomial, exponential function, sine or cosine, with the constant coefficient, you can use the method of undeterminate coefficients. Otherwise, variation of parameters all the time, okay? So that's going to be the case. So the variation of parameter method can be applied to find a particular solution, okay? Can be applied to find a particular solution. We know that's going to be YP. Okay, YP of a non-homogeneous, non-homogeneous second order, the linear equation, okay? Of course, it can be done for any order. So of a non-homogeneous, I just go with the linear equation. Okay, linear equation. But the one that we're going to be interested in should have the following form. Y double prime as px y prime plus qx y. So again, the coefficient of y double prime must be 1. It is equal to the r of x. Okay, this is the one we usually refer to as equation number 1. Okay, the way we are going to do it, we are going to use solve the homogeneous one first. Okay, so what we are going to do is we are going to suppose you already done. Suppose it doesn't matter which form R. There's going to be a method that you're going to find the YC. So suppose the YC, you get it, and it's the C1 and Y1. That's C2, Y2. Okay, is going to be the general solution. Is the general solution as usual of the corresponding homogeneous equation of the homogeneous equation associated to this one. And you know that we refer to it as a y double prime plus px y prime plus qx y equal to this. Call it the equation number 2. So we already done with this one. Somehow, whatever method, we already got the YC. And what we're going to do is, that's why we call it variation of parameters. You see in this equation, you have 2 constants in this solution. C1, okay, you have 2 constants, C1 and the C2. So what we're going to do is, we are going to replace this C1 and C2 by 2 functions. We usually call it U1 and U2. Okay, so we change the parameters, if you like, C1 and C2 into the 2 functions, U1 and U2. Then we force this one, okay, to be a YP for us. Okay, so we assume that the solution that we're going to be interested in We introduce yp to be equal to the u1 y1 plus u2 y2. Then we investigate under what condition on the u1 and u2 this form is going to be a particular solution. Okay, so as usual, we force it to be a solution that we are going to be interested in. As we move on, you know that it's going to be a solution if it's satisfying the equation. So we just plug it into the equation, and eventually we are going to get a formula for the U1 and U2. You memorize those formula and done. Okay, it's nice to be able to create that formula. So that's the idea. That's why we call it variation of problems. And we do exactly the same when we get to the system of the equation at the end of the course. Okay, so I propose a question and then I answer that question. You see, you better understanding of what's going on. So the question is going to be that can be, okay, let's say can, or is there, can two functions u1 and u2, okay, u1 and 2 be formed, if you like, with this condition, so that yp equal to u1 y1 plus u2 y2 is going to be the particular solution of the equation. Okay, is going to be a solution. Okay, a solution of the homogeneous. Okay, it's going to be a particular solution. A particular solution is a particular, all a solution is the same thing. Okay, is a particular solution of the non-homogeneous equation. Okay, of the equation number 1. Okay, so that's a question that we're going to answer. Or we want to investigate under what condition you can find the U1 and U2, so that this combination is going to be a particular solution of your equation. Okay, now we are going to investigate to see what condition do we do it. Okay, so I want to, it's going to be solution of the equation. So I would like to plug in into this equation number 1. So I need the y prime and the y double prime. Okay, so patiently find the y prime and yp prime and yp double prime of this. Okay, so there you are. So what I'm going to do, I'm going to find what is going to be yp, y prime p, and what's going to be y double prime p. I already got the yp. Okay, then I substitute into number 1. So I start differentiating. Okay, and the yp is already given. Okay, so I repeat the yp. So my yp is u1 y1 plus u2 y2. So u1, u2, y1, y2, they are all differentiable function of x. Okay, differentiate. What is going to be yp prime equal to? Okay, product rule all over the places. The first one, you have to have the first, second, first. So it's going to be u1 prime times y1 plus the second times first. u1 y1 prime. Okay, so that's going to be the first part. Then we're going to do the same thing to the second one. So it's going to be plus. I start with the second one. Same thing, u2 prime times y2. Okay, times y2 plus u2 times y2 prime. Okay, that's a derivative of the first times second plus derivative of the second times okay, times it by the first one. So that would be our yp prime. So what we'd like to do is we'd like to take the second derivative. Okay, to take the second derivative. You see, we are going to think about it. How many unknown are we going to have? See, our unknown are going to be u1 and the u2. Since they are unknown, when you substitute, you are going to have a new differential equation. Your new differential equation would be what? your new differential equation would be involve U1 and U2. So if we just keep it as is, if you want to find the second derivative, what's going to be the second derivative? If you want to find the second derivative, again, it's going to be, you just, you have to apply the derivative of the first, second, first, okay, and then you continue. So look at these. So we would like to avoid a new order of the differentiation, if you like. So what I'm going to do is, I'm going to pick this, put this U1 and the U2 together, okay, and collect it. Let's put it together, make it easier to handle. Because this would be difficult. If you differentiate it as is, you get to the U1 double prime, U2 double prime. Original equation is the equation of a second order. So you create something which is going to be more complicated. You won't be able to handle it. So what we are going to do, we are going to rewrite it. Okay, this is the way I'm going to rewrite it is going to be, I'm going to, you see U1 find, U1, Y1 prime, then U2, Y2 prime. I take these two, because if I want to differentiate again, then I get to the U1 prime and U2 prime. So what's going to be the leftover? You see the leftover would be what? The leftover as what? The leftover is going to be, I got the U1 prime Y plus U2 prime, U1 prime Y1, okay, plus U2 prime Y2. I group them together to get these numbers. Now, we want to differentiate this one. In order to simplify our procedure, this is up to us what we want to do. So what we do is we impose a new condition. The new condition is we assume that we are going to find the U1 and the U2 so that this second part would be 0. Okay? If this second part would be 0, you drop it and you'll be able to continue nicely to get those numbers. Okay? So the reason is if you want to go to the second derivative, you see there are going to be second derivative of U1 prime, U2 prime, so complicated. You won't be able to do it. So this is up to us. Say, okay, this is the first condition that I'm going to impose. So we are going to suppose you're not going to lose anything. This is because up to you. As long as you prove that they are the solution of the equation, you'll be fine. So we are going to suppose U1 prime Y1 plus U2 prime Y2 is equal to the 0 from now on. And I told you the reason. The reason is we want to avoid the second derivative for the U1 and the U2. So, so now we are going to have new Y1 prime. So from now on, YY prime would be what? Y1 prime would be U1 Y1 prime plus U2 Y2 prime. So this is going to be our Y prime. Any question? Now continue. Now find the second derivative. That would be easy. Yes.
Why are we allowed to assume that that ends up being 0?
Who can prevent it? We assume it. No, you see, because you have to find it eventually. You have to find the U1 and U2 yourself. And you just keep going to see what is going to be the condition that you need to be able to find. You see, if you keep it, look at this one. If you keep it, if you want to find the second derivative, just imagine what are going to happen. If you get 7 to get the U1 double prime, U2 double prime, then you go back and substitute the original. You have to substitute the original equation. When you substitute, you face with the new second order differential equation. Okay. And you don't know how you're going to solve that one. So that's why it doesn't matter. As long as you prove your theorem, you can impose the conditions. If these conditions are going to be nice, you keep it. If it's not, you come back, okay, and revise it. This is the way you do the proof, okay? At the end, as long as the logic and everything is going to be consistent, nothing to worry about. Okay, now let's find the second derivative. Differentiate again. So we go to the Y double prime, okay? Y double prime of P is equal to the product rule again. derivative of the first times second, that give you u1 prime. y1 prime plus u1, you see, get y1 double prime. For the y, it's okay to get the y double prime. Because y1 and the y2, remember, are solution of the homogeneous equation. So we can take care of that, but not for the u1. Okay, so that's the first one. Continue. Second one, repeat it again. Derivative of the first, second, first. u2 prime, y2 prime plus u2. You see, y2 double prime is also okay because we have something to take care of it for this. Okay, so this is going to be a situation that you are going to have. So this is going to be y double prime. There you are. You are ready. Go to the non-homogeneous equation. You want the yp to be the solution. Substitute. You substitute. This is your equation that I'm going to see. This is equation number 1. Since yp is the solution of this equation, so yp should satisfy this equation. So the yp, y prime, and y double prime. You substitute, they must be 0. Then we can find that equation. Okay. So this is it. Today we're going to talk about it. Okay, this is it. And note that yp is a solution. It's going to be a solution of the equation. Just remind you, what is the equation? Equation number 1, y double prime plus px times y prime plus qx y equal to the r of x. This is the equation number 1. Remember. Now substitute. Substitute. So this is going to be, so it should satisfy the equation. Okay. It should satisfy the equation. Now substitute y double prime. Go to what that we did. Y double prime was this one. Is y1 double prime u1 from the previous part. y1 prime u1 prime plus u2 prime y2 prime plus u2 y2 double prime. It's the one that I got from the previous part. Okay, that's a y double prime. Continue, plus px, p of x times y prime. So what was the y prime? Y prime p was u1, y1 prime plus u2, y2 prime. So that is yp double prime, that's the yp prime, plus qx times yp. So plus qx times the yp. What's the yp? u1, y1, u2, y2, and this must be equal to the r of x. Okay, so we substitute. We plug in all the, okay, for the yp, y prime, and the y double prime. Now we have to simplify it. Remember, y1 and y2 is what? y1 and y2 are solution of the homogeneous equations. So try to put them together so that you'll be able to take care of this. Look at this. I'm going to take care of the y1 pair. I have, you see, I want something like this, but I want it for y1. So this is my y1 double prime. Okay, so I need y1 prime u1. You see px, that's a px, and this is it, y1 prime. So I put these two together. Then I need something for the q. So I need a q of x, y1 u1, q of x, y1 u1. Okay, just put these 3 terms together. So what are you going to have? If you put 3 terms together and at the same time factor out the u1, so I factor out the u1, that give me y1 double prime, px y prime plus qx y1. See? factor out, you see this term that are underlined here. See the inside? What is this? Okay.
Second order.
Oh, remember y1 is what? y1 is the solution of the homogeneous equation. So the equation is what? Homogeneous equation.
0.
Y double prime pxy prime plus qxy equal to the 0. So this means this would be 0 because y1 is the solution of the homogeneous equation. That would be all. Okay. Now we are going to make something similar for the y2. Okay. So let's check the y2. What we have for the y2. We start with the double prime. This is it. This is y2 double prime. We need px times y2 prime. This is it. And then we need the qx times y2. So the one that I underlined with the red, okay? So I pull out a u2, u2. So the leftover is going to be again y2 double prime, px y2 prime plus qx y2. You see? Again, since the y2 is the solution of the homogeneous equation, this would be 0. Okay? So what's the leftover? That leftover is the one that you know you need. What's going to be the leftover? So everything cancels out except, you see, this is it, except these terms that you see over here. Okay, so we put them together. The leftover is going to be, you see, this was also, just check, yeah, this is it. Only these two. You see, only you get these two on this side and the R of x on the other side. So there you are. You are going to have y1 prime u1. u1 prime plus u2 prime y2 prime. This must be equal to the R of x. See? So this is going to be your condition for the u1 and the u2 to be, okay, for that yp to be the solution of your equation. But remember, we already imposed one condition ourselves. You have two unknowns to find. You have to find the u1 and the u2. This is one condition. And the other one, remember, the other one is what? This is it. This is the one that we assume it will be equal to the 0. So put them together, that gives a system of the equation, and you'll be able to solve it, and you get the final answer. So the conclusion so far is going to be, in order to have the solution, therefore, put those two systems together. There you are. The one that you let it equal, that was why I just let that to be equal to the 0. This is the one that we did previously, okay? u1 prime y1, u2 prime y2 equal to the 0. And this is the second one. y1 prime u1 prime plus u2 prime y2 equal to the R of x. That's it. Remember, the unknown are going to be u1 and the u2. We have a system of the equation in which the unknown are u1 prime and the u2 prime. Solve this system of the equation. It's a system of two equations, two variables. Any suggestion? How can solve it? Elimination method. Elimination method. How can solve it? Okay. Suppose you want to eliminate which one? u1 prime. If you want to eliminate u1 prime, you have to multiply the first one by y1 prime, okay, and the second one by y1. You have to change the sign of one of them, okay? It doesn't matter which one is it. So I'm going to change the sign of the first one. So this is going to be the conclusion. So you are going to have what? u1 prime, y1 prime, and plus u2 prime minus u2 prime, y1 prime, y2 equal to the 0. And for the second part, you are going to have a u1 prime, y1 prime, okay, plus u2 prime, y1. Must be something wrong with this.
Minus in the first one.
Sorry?
Minus in the first one. When you distribute.
Yeah, that's gonna be minus. Okay, that's gonna be the minus. So I multiply the y prime here. And the second one, this is going to be, did I miss any sign here? Yes. You see this r of x, this is prime here. This is prime here, okay? y2 prime. y2 prime, so this is now going to be y1, y2 prime. y2 prime equal to the r of x. Okay, now, there you are. The first one will disappear. The second one, I'm going to add them together. At the same time, I factor out the u2 prime. Okay, I factor out the u2 prime. So I'm going to have y1, y2 prime minus y1 prime, y2 equal to the r of x. What is this coefficient? Remember?
Is that the Wronskian?
That's a Wronskian, yes. Okay, so this is going to be simply the Wronskian. Remember W, the W of y1, okay, the W of y1 and y2. In short, we call it W. So we get the u2 prime, that's it. So the u2 prime would be what? u2 prime would be r, oh, I missed something here. That's it going to be u2 prime. I multiply, remember I multiplied the second one by y1. So I should multiply by y1 here as well. Okay, so this is going to be y1. Now we are okay. So what's going to be u2 prime is going to be on the top. Is going to be y1 times r of x divided by the Wronskian. So that would be u2. u2 prime. Remember, you are looking for u2. So integrate it. So what's going to be u2? So the u2 would be what? u2 would be the integral of, easy formula to remember, y1 r of x divided by the Wronskian d of x. See, it's a u2, but this is y1. Remember, the y1 is your solution of the homogeneous part. So you already got the y1 and the y2. You find the Wronskian. You are going to form this integral carefully, and then you find it. If this integral happened to be complicated, probably you miss the p of x. You see, all those famous problems that we have, the y double prime coefficient is not 1. It's something else, x squared, x cubed. So make sure you do it. Okay, so that's going to be 1. Similarly, if you believe it, you can find similarly, your u1 would be this one. So that's a u2. So the u1 is going to be a negative sign here. Okay, it's going to be negative y2 times r of x over the Wronskian. That's it. So we have the u1 and the u2. So nicely we can write y of p equal to the u1 y1 plus u2 y2 is going to be, y2 is a particular solution. Okay, it's going to be a particular solution. And of course, you know that y equal to the yc plus yp is going to be your general solution. And then, okay, and then do that. Get these numbers. Okay, it's very nice method and easy to apply really. I just prove it for you so that you see it, because we are going to have it, what the system of the equation is going to be kind of linear algebra format. It's a very nice one. So when we get to that part, we can quickly take care of it because we already proved it and we have the idea of, we write it down in terms of the matrices. It'll be easier, okay? So this is it. This is a method of the variation of the parameter. So let's see if we can quickly give you one example and then we're done. Yes.
So we find Y1 based on what we already know in the past. And then we use that to plug it in.
Yeah, you need to have the Y1 and the Y2. So if it's going to be, most of the time, it's going to be an equation with a constant coefficient. But on the other side is not sine, cosine, e to the x.
It's just 0.
It's mostly, no, not 0. It's going to be non-homogeneous one,
Okay.
okay? The nice one is tan x, secant x, okay? Secant, cosecant, because the sine and the cosine, you can do it with the undeterminate coefficient. So, they put it something like this. So if it's going to be possible to find the solution, they give it the solution. There's going to be another type that we call it Cauchy-Euler equation. The coefficients are not constant, but there is a nice method to be able to take care of the Y1 and the Y2. So you have it or you find it, but it takes time because the full equation will be given to you. You have to find the homogeneous one first, then patiently find the YP, put them together, okay? It's a nice method, okay? Take care of it. Okay, let's see if I can give you quickly one, and then there are a couple of nice ones when I post the extra practice one. I have a group of them that we have all the possibility for the integration. Let's make sure you do it, and as I told you, make sure that don't miss the YC. So let's see if we can quickly do one example, and then we give you more next time. So we are done with solving the linear equations. I'm not going to do anything else, but there is a special group, we call it Cauchy-Euler, we're going to talk about it. And then before the next test, they were all linear. So what are we going to do when they are not going to be linear equation? So we take care of that one, okay? So there you are. It's a true problem, but let's see if we can do one of them. Find the general solution. General solution of the equation. I have 3 examples, but I'll give you one of them today, then the rest next time. Let's see. This can be done quickly. It's very famous one. 1 over sine. Cosecant, I just write down 1 over sine. Okay, cosecant, secant, tangent, the possibilities. Okay, there you are. First thing to do, you have to solve a homogeneous, okay? So solve, have to find the YC. That's easy to solve. Okay, characteristic equation is going to be r squared plus 1 equal to the 0. So r squared equal to the -1, which is I squared. So r would be positive negative I. Take the positive one I, and this is going to be 0 plus I, alpha plus beta I. So the alpha is 0, beta is 1. Okay, so the corresponding solutions are going to be y1 is going to be e to the 0 cosine of x, which is just cosine of x, and the y2 would be e to the 0, okay, sine of x, which is sine of x. Okay, so it's going to be y1 and y2, and you declare the yc. Yc is going to be what? It's going to be c1 cosine of x plus c2 sine of x. So this is going to be your solution to the homogeneous one. Any question? For the rest, you have to find the YP. Okay, we check the YP. The coefficients are constant, but R of x is not those 3 categories that we have. Remember, exponential one, trigonometric sine or cosine, or a polynomial. So you realize that the variation of parameter method must be applied. Okay, that's the choice that you have, unless you've been told. Variation of parameter. Okay, parameters should be applied, okay, or can be applied. Okay, so you cannot use the undetermined coefficient for this one because of the R of X. So there you are, you identify for this method, you identify the y1, which is cosine of X, y2, which is sine of X, R of X. You check to see if you have to divide by something. The coefficient of y double prime is already 1. So R of X is simply 1 over sine X or cosecant of X. Okay? So you introduce the YP. YP would be equal to the U1 Y1 plus U2 Y2. There or when your U1, remind yourself, is a negative Y2 R of X divided by the Wronskian X, and your U2 is integral of Y1 R of X divided by the Wronskian. These are your formulas. So you have to find the Wronskian first. Okay, so you know that the Wronskian is Y1, Y2 prime minus Y1 prime, Y2. So bring the Y1 prime. Your Y1 is cosine of X. So Y1 prime is negative sine X. Okay, continue. Your Y2 is sine of X. So Y2 prime is cosine of X. Forget the Wronskian. Now that you cross multiply. Y1 by 2 prime. So that would be cosine of X times cosine of X minus the other way around. Y2, Y1 prime. Or Y1 prime, Y2. Negative sine times sine. It's usually easy result. So that gives you cosine square plus sine square. Cosine square of X plus sine square of X, which is equal to 1. The Wronskian is 1, and the integral should be done easily. Any question? So carefully get the Wronskian, double check it. Yes.
Is Y1 and Y2, those are given, you said? Y1 and Y2 are given?
No, you have to find it yourself. See, we did it. So in order to solve the equation, you know that you have to solve the homogeneous one first. So as soon as you solve the homogeneous one, you have the Y1 and Y2. This is the way I call it Y1 and Y2. You may do it the other way around. It doesn't matter. But you have to find it. Okay, now we are ready to get the U1. Okay, so this is the where you have to be careful. Okay, I'm going to use the U1. Okay, so there you are. The U1 is negative Y2 R of X divided by the Wronskian. Substitute negative Y2. What is the Y2? I take the Y2 to be sine X, okay? So that would be negative sine X times R of X. R of X is 1 over sine X. Wronskian is 1. Here you go. Nicely would simplify. So that gives what? Integral of just a negative 1. Which is going to be negative X. Remember, they are particular solution. You're not going to add the constancy. They are particular solution. So that gives you U1. So the U1 would be negative X. Any question? Go back, repeat the formula for U2. U2. U2 is integral of Y1 R of X divided by the Wronskian. So Y1 is cosine. R of X is 1 over sine. And the Wronskian is 1. Okay, so that give you integral of cosine x over sine x. Any suggestion? What's this integral?
Cotangent.
Cotan, you see u prime. Derivative of a sine u, you get sine, derivative of a sine is on the top. So it's simply, you can go with the ln of the absolute value of sine. Okay, that's going to be fine. So u prime u to give the result. So the tangent secant q is our popular part of the day. Okay, and there you are. Remember, no constancy. So we are ready to give you the YP. So what's a YP? YP is U1 Y1 plus U2 Y2. Substitute. U1 is a negative X, Y1 is, okay, what is the Y1? Cosine. And plus U2. U2 is ln of the absolute value of the sine times it by the Y2, which is sine x, yes. You have to simplify if you can. In this case, there is no chance to simplify it. Okay, so there you are. Just repeat it because put the sign in up in front. Sine x ln of the absolute value of sine x. That's YP. The general solution y1 plus y equal to the yc plus yp. If you want to write it, it's up to you. If you write this, we accept it, of course. So if you want to repeat it, this is it. C1 cosine x plus C2 sine x minus x cosine x plus sine x ln of the absolute value of sine. This is going to be the general solution of the equation. It's a very nice technique, nice method. You see it. Okay, so there are going to be a couple of tricky ones, especially if you put that, replace it by secant would be more interesting. So we give you a couple of more examples. That we are done. This is section 4.6. Then we go to the 4.7, very special equation.